We learned that the area of a square equals side times side. Suppose we have a side of a square in centimeters, that is 1. So the area will be 1 times 1. We can write this as 1 square, and we simplify as 1. What about if the side is 2? The area is 2 times 2, or we write as 2 square, and we simplify this as 4. If the side is 3, the area is 3 times 3, or 3 square, and we simplify as 9. What about the side of 5? The area is 5 times 5, or 5 square, and we simplify this as 25. If the side is 8, the area is 8 times 8, or 8 square, and this is 64. So if the side is A, the area is A times A, or A square. Such numbers like 1, 4, 9, 25, and 64 are known as square numbers or perfect squares. In general, if a natural number m can be expressed as n square, where n is also a natural number, then m is a square number. Hi everyone, today we're going to study some properties of square numbers. Here we have a table of number and their corresponding squares. We put here numbers from 1 up to 25 along with the squares. Also the numbers 30, 35, 40, 45, and 50 along with their squares. Let us see some properties. Look at the square numbers ending in 1. These are examples. The squares are 1, 81, 121, 361, and 441. If we write the corresponding number, for square of 1, the number is 1. Square 81, the number is 9. Square is 121, the number is 11. The square 361, the number is 19. And the square number 441, the number is 21. In this case, we will say that if a number has 1 or 9 in the unit place, then its square ends in 1. Another property for square numbers ending in 6. These are the examples. For a square of 16, the number is 4. For a square number of 36, the number is 6. For a square number of 196, the number is 14. For a square number of 256, the number is 16. Then we conclude that when a square number ends in 6, the number whose square it is will have either 4 or 6 in unit place. What about numbers ending with zeros? Look at the first 3 examples. For number 10, the square is 100. For number 20, the square is 400. For number 80, the square is 1600. For the number with 1 zeros, the square will have 2 zeros. What about the 4th, fifth and sixth example. For 100, the square is 10,000. For the number 200, the square is 40,000. For the number 800, the square is 160,000. Look at the numbers. There are 2 zeros. The squares will have 4 zeros. Now we conclude. When a number ends in n number of zeros, its square number ends with 2n number of zeros. Here is another property. The square of an even number is an even number. For number 2, the square is 4. Number 4, the square is 16. For number 6, the square is 36. The square of 8 is 64. The square of 10 is 100. These are even numbers, and the corresponding squares are even numbers respectively. And we say that the square of an odd number is an odd number. This is our table for examples. The number 1, the square is 1. The number 3 has a square 9. The square of 5 is 25. The square of 7 is 49. The square of the number 9 is 81. These numbers are odd numbers, and the corresponding squares are odd numbers respectively. Hi everyone. Today we're going to study triangular numbers. Triangular numbers are numbers whose dot patterns can be arranged as triangles. Let's have some examples. The number 1 corresponds to 1 dot, and this is the first triangular number. Another number is 3, corresponding to 3 dots. Then we arrange the 3 dots in this way so that it will look like a triangle. Another example is the number 6 that corresponds to 6 dots. The 6 dots are arranged like this to make it look like a triangle. Another example is the number 10 with 10 dots, and this arrangement looks like a triangle. Another number is 15, corresponds to 15 dots, and the 15 dots are arranged in such a way that it looks like a triangle. Now we do adding triangular numbers. Let us remember some examples of triangular numbers, and this is the principle in adding triangular numbers. In adding 2 consecutive triangular numbers, the sum is a square number. Let us see some examples. Suppose we have this 1 and 3, and we write here 1 plus 3. If we put together the dots, it will appear like this. It looks like a square. We know that 1 plus 3 equals 4, and this 4 is equal to 2 square. Another example, what about this 3 and 6? So we have 3 plus 6. If we arrange the dots, we can do it like this to look like a square. The 3 plus 6 equals 9, and this 9 is a square number that is corresponding to 3 square. Another example, what about the 6 and 10? That is 6 plus 10, and this corresponds to 16 dots. We arrange it like this to look like a square. The 6 plus 10 is 16, and we know that this 16 is a square number that corresponds to 4 square. By these examples, we affirm that in adding two consecutive triangular numbers, the sum is a square number. Hi everyone. Today we're going to study numbers between square numbers. The numbers 1, 4, 9, 16, 25, 36, and so on are examples of square numbers. Suppose we list the numbers from 1 up to 25. Then we identified the square numbers. 1, 4, 9, 16, 25 are here. Now the question is, how many non-square numbers are there between two consecutive square numbers? For example, the numbers 1 and 4. We count the numbers in between these two consecutive square numbers. The numbers are 2 and 3. So we have two numbers between the numbers 1 and 4. What about the numbers between 4 and 9? So the numbers are 5, 6, 7, and 8. So we have 4 numbers between these two consecutive square numbers. Another example, between 9 and 16. The numbers are 10, 11, 12, 13, 14, 15. So 1, 2, 3, 4, 5, and 6. There are 6 numbers between 9 and 16. What about between 16 and 25? So the numbers are 17, 18, 19, 20, 21, 22, 23, 24. That is 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 numbers between 16 and 25. And then let us generalize. First, let us show this table. For the first column, we write the natural numbers. For the second column, we square that particular number. So this is 1, the square is 1, 2, square is 4, 3, the square is 9, 4, the square is 16, 5, the square is 25, and so on. So we write here for a to be n square is a square. Now this is the rule. In general, there are 2n non-perfect square numbers between the squares of the numbers n and n plus 1. Let's see this example. How many non-square numbers are there between 9 and 16? So 9 here, we can write as 3 square. Look at our table. The 9 is here, that corresponds to the number 3 as the n. And we write n equals 3. For the number 16, we can look also at our table. So the 16 is here, and we can write as 16 equals 4 square. So the corresponding value for 16, the n is 4. However, in this problem, since n equals 3, n plus 1, that is the number 4. In a problem like this, we are only concerned about the n. Based on our principle here, we will use this formula 2n to know how many non-perfect square numbers are there between the two consecutive squares. So 2 multiplied by 3. Our n is 3. So that is 6. So that means there are 6 non-square numbers between 9 and 16, as it is shown in our example here. Another example. How many non-square numbers are there between 25 and 36? So we can see that these 25 and 36 are two consecutive square numbers. But since 25 is the smaller number, we write it here, and that is equal to 5 square. In this case, our n is 5. We use our formula 2n. That means n is 5, so we substitute it here. 2 times 5. And that is 10. That means there are 10 non-square numbers between 25 and 36. We can list them down. 26, 27, 28, 29, 30, 31, 32, 33, 34, 35. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Hi everyone. Today we're going to study sum of first odd natural numbers. Let us see this pattern. The first odd number is 1, and this is 1 that we can show that this is 1 square. What about when we have 1 plus 3? This is the sum of first two odd numbers, and the answer is 4, and the number 4 we can represent as 2 square. What about 1 plus 3 plus 5? This is addition of first three odd numbers, and the answer is 9, and the number 9 we can represent as 3 square. What about 1 plus 3 plus 5 plus 7? This is addition of first four odd numbers, and the answer is 16. The number 16 we can write as 4 square. And then we have 1 plus 3 plus 5 plus 7 plus 9. This is addition of first 5 odd numbers, and the answer is 25. We represent 25 as 5 square. Then we have 1 plus 3 plus 5 plus 7 plus 9 plus 11. This is the sum of first 6 odd numbers, and the answer is 36. And this 36 we can represent as 6 square. With this pattern, we can conclude that the sum of first n odd natural numbers is n square. Also, we can say that, conversely, a square number is the sum of successive odd numbers starting from 1. Example 1. Find the sum of the first 10 odd natural numbers. We know that this is our formula. The sum of first n odd natural numbers equals n square. Our problem is about the sum of first 10 odd natural numbers. Based on the formula, we can solve by 10 square and simplified as 100. This is the answer. Example 2. Find the sum of the first 20 odd natural numbers. Our formula is simply we get n square. So the first 20 odd natural numbers, that will be 20 square, and we simplified as 400. This is the sum. Hi everyone. Today we're going to study square of odd number as sum of consecutive natural numbers. Let's see this example. Suppose we have number 3 and we square this. The answer is 9. And this 9 we can represent as 4 plus 5. Note that this number 4 is the same with 3 square minus 1 all over 2, while the number 5 is the 3 square plus 1 all over 2. In general, for any odd natural number n, the n square equals the sum of n square minus 1 all over 2 and the other n square plus 1 all over 2. Now we want these two consecutive natural numbers. We can simplify the computation. To find the two consecutive natural numbers, let's say the first number is x while the second number will be x plus 1. As addends, for square of odd number n, divide n square by 2. And then the integer part of the resulting decimal is the value of x. When we get the value of x, we can easily get the x plus 1 or the second consecutive number. Let's see more examples. Suppose we have 5 and we want to square this, and this is equal to 25. Let us find the two consecutive natural numbers. What we do is, this 25 we divide by 2, and the answer we will get as 12.5. This 12, the integer part, is the first integer, plus 13. So 12 plus 13, these are the two consecutive natural numbers, and the sum is equal to the square of 5. Another example, 7 square, that is equal to 49. 49 divided by 2, we will get 24.5. This 24, or the integer part, is the first number, plus the second number will be the consecutive number, which is 25. So 49 equals 24 plus 25. Another example, 9 square equals 81. Let us find the two consecutive natural numbers. So this 81 we divide by 2, the answer is 40.5. The number 40 is the first integer, plus the consecutive integer, which is 41. So 81 equals 40 plus 41. Another example, 11 square equals 121. Let's find the two consecutive natural numbers. We divide 121 by 2 and the answer is 60.5. The number 60 is the first integer, plus the 61. So 60 plus 61, that is 121. 15 square equals 225. So the two consecutive natural numbers, we do again the usual process. We divide 225 by 2 and the answer is 112.5. This 112 is the first integer plus the next integer 113. So the 225 is equal to 112 plus 113. With these examples, again we say that we can express the square of any odd number as the sum of two consecutive positive integers. Let's see this example. We have here 11 times 13. These are two consecutive odd natural numbers, and the product is 143. Now let us analyze the 11 times 13. The number between 11 and 13 is 12. This 11 is 12 minus 1 times the 13 with respect to the middle number, that is 12 plus 1. Now let's apply our special product in this multiplication. So we have 12 square minus 1 square. When we simplify, 12 square is 144 minus 1 square, which is 1. 144 minus 1 equals 143, which is the same answer as what we have earlier. In general, this is our formula: a minus 1 times a plus 1 equals a square minus 1. In words, the product of two consecutive even or odd natural numbers is equal to the square of the middle number minus 1. Let's see more examples. 13 times 15. The middle number is 14. Based on our formula a while ago, we will write 13 times 15 as 14 square minus 1. 14 square is 196 minus 1, and the answer is 195. This is the product for 13 times 15. Another example, 29 times 31. The middle number is 30. So we write 30 square minus 1. The square of 30 is 900, then minus 1. This is equal to 899. Another example, 44 times 46. The middle number is 45. So we write 45 square minus 1. The square of 45 is 2025 minus 1, and the answer is 2024. Next example, 18 times 20. The middle number is 19. In our formula, we write here now 19 square minus 1. This 19 square is 361 minus 1, and the answer is 360. Example 5. 6 times 8. The middle number is 7. So we write here 7 square minus 1. 7 square is 49 minus 1, and the answer is 48. Hi everyone. Today we're going to study pattern for squares of 1, 11, 111, and so on. Observe the squares of 1, 11, 111, and so on. Let's begin with 1 square. The answer is 1. Next, 11 square. The answer is 121. And we write the answer this way. Next is 111 square. This is equal to 12,321. And we write the answer in this manner. Next, 1,111 square. And this is the answer. 1,234,321. Next is 11,111 square. And this is the answer. Next number is 111,111 111 square. And this is the answer. But we are writing the answer in this manner. Now let us observe the squares. Note that the square digit is forming a beautiful triangular pattern. Each square number starts with 1 and ends with 1. For 1 square, it's 1. 11 square, 121. Starting with 1, ending with 1. Starts with 1, ends with 1, and so on. Now looking at the arrangement vertically, the top number is 1 and the numbers are increasing while going down. For the first number here, it is 1. For this column, we have 1 and 2. For this column, 1, 2, 3. This column, 1, 2, 3, 4. This column, 1, 2, 3, 4, 5. And this column is in the middle. So we see that 1, 2, 3, 4, 5, 6. All the other columns follow the pattern. The number of digits for each of the square is odd. For 1 square, there is only 1 digit. 11 square, 3 digits. 111 square, 5 digits. 7 digits. 9 digits. 11 digits, and so on. Let us observe the squares of 7, 67, 667, and so on. Let's begin with 7 square. The answer is 4 and 9. Please observe that this number starts with 4 and ends with 9. Next is 67 square. The answer is 4,489. This number starts with 4 and ends with 9. And there is a number of 4 and 8 in between 4 and 9. Next is 667 square. And this is the answer. Note again that the number starts with 4 and ends with 9. In between, there are pairs of 4 and 8. This is the first pair, 4, 8. And this is another pair, 4, 4 and 8. Now we can conclude. For every digit 6 on the number, we have here 2 digits of 6. There is a pair of 4 and 8 in each square. Since we have 2 digits of 6, there are 2 pairs of 4 and 8 also. Now 6,667 square. And this is the answer. The number starts with 4 and ends with 9. In between, there are pairs of 4 and 8. This is the first pair of 4 and 8, another pair for 4 and 8, and this is the third pair of 4 and 8. We have here 3 digits of number 6. It corresponds to 3 pairs of 4 and 8. What about 66,667 square? This is the answer. This number starts with 4 and ends with 9. In between, there are pairs of 48. This is the first pair of 4 and 8, second pair of 4 and 8. This is the third pair, and the fourth pair. We have here 4 digits of number 6, it corresponds to 4 pairs of 4 and 8. Next number, 666,667 is square. And this is the answer. The number starts with 4 and ends with 9. In between, there are pairs of 4 and 8. This is the first pair. Second pair, third pair, fourth pair, fifth pair. There are 5 digits of number 6. It corresponds to 5 pairs of 4 and 8. Notice also that the number starts with the number 4 repeatedly, followed by the number 8 repeatedly, and at the end, it ends with number 9. Hi everyone. Today we're going to study pattern for squares of 11, 101, 1001, and so on. Observe the squares of 11, 101, 1001, and so on. Let's begin with 11 square. We know that the answer is 121. Let us observe the square. Notice that the square number starts with 1 and ends with 1. The middle number of the square is 2, so 121. Next, let's have 101 square. This is the answer, 10,201. Let us observe this value. The square number starts with 1 and ends with 1. The middle number of the square is 2. Now note this. For every 0 on the given number, our given number is 101, there is 0 in the second digit. There is a corresponding 0 before and after the number 2 of the square number. There is 1 0 here, so there is 1 0 before 2 and after the number 2. So 101 square is 10,201. This is now the pattern for our squares of 11, 101, and 1001 and the like. Let's see 1001 square. This is our answer. The square number starts with 1 and ends with 1. The middle number is 2. And then, since there are 2 zeros in the given number, there are also 2 zeros before the number 2 and after number 2. Next number is 10,001 square. This is our answer. The square number starts with 1 and ends with 1. The middle number is 2. In the given number, there are 3 zeros here. So, for the number 2, there are 3 zeros also before this number and after the number 2. Next, 100,001 square. This is the answer. The square number starts with 1 and ends with 1. The middle number is 2. In the given number, there are 4 zeros here. So we write 4 zeros before number 2 and after the number 2. Hi everyone. Today we're going to study pattern for squares of 101, 10,101, 1,000,000, 10,101, and so on. Let us observe the squares of these numbers. Notice that the given number is an alternating 1 and 0 that starts with 1 and ends with 1. Let's begin with 101 square. And this is the answer, 10,201. Let us observe this answer. This square number starts with 1 and ends with 1. This number is an alternating of significant numbers and 0. You see here, 1, 0, 2, 0, 1. The significant numbers are increasing and decreasing by 1. So it starts with 1, followed by 2. After that, it ends with 1. The highest significant number in the square, which is in this example is 2, is equal to the number of ones in the given number. Our given number is 101. The number 1 appears twice, so the number 2 comes here as the highest significant number. Let us see the next example. 10,101 square. And this is the answer, 1,0,2,0,3,0,2,0,1. Notice that the square number starts with 1 and ends with 1. This number is an alternating of significant numbers and 0. The significant numbers are increasing and decreasing by 1. So we have here 1, 2, 3, then 2, then 1. The highest significant number here is 3 because in the given number, the number 1 here appears 3 times. Another example, 1,010,101 square. And this is the answer. The square number starts with 1 and ends with 1. This number is an alternating of significant numbers and 0. See here, 1, 0, 2, 0, 3, 0, 4, 0, 3, 0, 2, 0, 1. The significant numbers are increasing and decreasing by 1. Notice that our highest significant number here is 4 because in the given number, this number 1 appears 4 times. So number 4 is coming as the highest significant number. Last example, let's have this number and let us square this. And the answer is 1,0,2,0,3,0,4,0,5, 0,4,0,3,0,2,0,1. Notice that the answer or this square number starts with 1 and ends with 1. The square number is an alternating of significant numbers and 0. The significant numbers are increasing and decreasing by 1. So we have here 1, 2, 3, 4, 5, 4, 3, 2, 1. The highest significant number here is 5 because in the given, the number 1 appears 5 times. Hi everyone. Today we're going to study pattern for sum of squares of this form. N square plus the square of n plus 1 plus the square of the product n times n plus 1. Let's note that the n here is a natural number. In this pattern, we're getting the sum of 3 squares. Let us see more notes. The bases of the first 2 squares are consecutive. We are referring to this first base, which is n, and then n plus 1 as the second base. Now the third base is the product of the first 2 bases. So n times n plus 1, that is squared. Let us see one example. 1 square plus 2 square plus 2 square. In the first square, the base is 1. Second square, the base is 2. Third square, the base is 2. Notice the first 2 bases. They are consecutive. This is 1 followed by 2. And the third base of this square is the product of 1 times 2, which is 2. 1 square is 1 plus 2 square is 4 plus another 2 square, which is 4. Finally, the sum is 9. Note that this 9 is 3 square. Then we can conclude. The sum is the square of the quantity third base plus 1. Our third base is 2 plus 1 becomes 3. Then we will square. Let us follow this pattern with other examples. What about 2 square plus 3 square plus 6 square? Notice that the first 2 bases are consecutive. The number 6 here, or the third base, is the product of 2 times 3. And the answer here is 7 square. So this is 6 plus 1 becomes 7. Then we will square. We can use our calculator to verify that the answer is 49 or 7 square. Another example, 3 square plus 4 square plus 12 square. The bases of the 2 squares are consecutive, 3 then 4. And this 12 is the product of 3 and 4. And the answer is 12 plus 1, and that is 13. Then we will square. Another example, 4 square plus 5 square plus 20 square. The bases 4 and 5 are consecutive. The base 20 here is the product of 4 and 5. And the answer is 20 plus 1, then 21. Then we will square. Another example, 5 square plus 6 square plus 30 square. 5 and 6 are consecutive. 30 is the product of 5 and 6. Then the answer, 30 plus 1 is 31. Then we will square. Last example, 6 square plus 7 square plus 42 square. The 6 and 7 are consecutive. 42 here is the product of 6 and 7. And finally, the answer is 42 plus 1, 43. Then we will square. Hi everyone. Today we're going to study finding the square of 2-digit number by splitting tens and ones. Let's discuss this lesson through examples. Example 1. Find the square of 23 without using the usual multiplication. So we have here 23 square. What we're going to do is to show this 23 as sum of tens and ones. So we have here the quantity 20 plus 3, that is squared. By the exponent, we're going to expand this expression. So we have 20 plus 3 times 20 plus 3. And by distributive property, we're going to multiply each of the terms of the first group to the second group. So we have 20 times the group 20 plus 3, then plus this number 3 times 20 plus 3. Next is this 20 outside, we will multiply to each of the terms of the group. Same thing we will do to the other group. So we have now 20 times 20 plus 20 times 3, then plus 3 times 20 plus 3 times 3. Then we simplify the corresponding products. 20 times 20 is 400 plus 20 times 3 is 60 plus 3 times 20 is 60 plus 3 times 3 is 9. Then the final sum is 529. Example 2. Find 39 square without using the usual multiplication. We write the 39 square, and this 39 we will show a sum of tens and ones. So we have the quantity 30 plus 9, that is squared. We expand the exponent, and we have 30 plus 9 times 30 plus 9. By distributive property, we will have this 30 times the quantity 30 plus 9 plus this 9 times the 30 plus 9. Then we multiply this 30 inside of the terms. Also for the 9, we multiply to 30, then to 9. So we have 30 times 30 plus 30 times 9 plus 9 times 30 plus 9 times 9. We simplify each of the products. So we have 30 times 30 is 900 plus 30 times 9 is 270 plus 9 times 30 is 270 plus 9 times 9 is 81. Finally, the total sum is 1,521. Example 3. Find 42 square without using the usual multiplication. Now this 42 we will show as sum of tens and ones. So 42 is equal to 40 plus 2, that is squared. We expand the square as 40 plus 2 times 40 plus 2. By distributive property, this 40 we multiply to the other group, then this 2 multiply to the other group. 40 times 40 plus 40 times 2 plus 2 times 40 plus 2 times 2. Then we simplify each of the product. 40 times 40 is 1,600 plus 40 times 2 is 80 plus 2 times 40 is 80 plus 2 times 2 is 4. Finally, the sum is 1,764. Hi everyone. Today we're going to study square of two-digit number ending in 5. Let's consider a two-digit number with unit digit 5. Let's say we have a5. This a here is the tens digit. Then let us square a5. When we show the tens and place digit of this a5, we will have 10a plus 5, and the quantity is squared. Let us expand this exponent into 10a plus 5 times 10a plus 5. Then let us expand. This 10a we multiply to the other group plus the 5 multiply to the other group. Then let us distribute. 10a times 10a is 100a square. 10a times 5 is plus 50a. Plus 5 times 10a is 50a. Plus 5 times 5 is 25. We can combine the two terms in the middle. 50a plus 50a is 100a. This first term, 100a square, is here. Then we copy plus 25 down here. Look at the first two terms. There is common on the two terms, and that is 100a, and multiplied by a plus 1. And plus the 25 we copy down here. We can write this 100 as a place value. So we have a times a plus 1. 100 plus 25. This is the answer when we square a5, or a two-digit number that ends with 5. In words, we say that in squaring a two-digit number ending in 5, the product has 25 as the last two digits, while in the hundreds place, we will write a times a plus 1. Note that this a here is the tens digit of the given number. Let's have some examples. We have here 3 examples: 25 square, 35 square, and 75 square. Let's begin with A, 25 square. We said that the product will be like this. It will end into 25. While in the hundreds place, look at our tens place here, which is 2, to be multiplied by the next digit to number 2, which is 3. So 2 times 3. So finally, the answer is 625, or 625. Next example, 35 square. So the answer will end at 25. And for the hundreds place, we have this tens digit 3 times the next number to it, which is 4. So 3 times 4 is 12 plus 25. It will be like this. Finally, the answer is 1225. What about 75 square? The answer will end at 25. And for the hundreds place, the tens digit is 7 times the next digit to it, which is 8. 7 times 8 is 56. Then we attach 25 at the end. So the answer is 5,625. This principle is applicable also with a 3-digit number. The answer will end at 25. And for the hundreds place, here it is 12, to be multiplied by the number 13. 12 times 13 is 156, and we attach the 25 values. So finally, the answer is 15,625. Hi everyone. Today we're going to study Pythagorean triplets. In the Pythagorean theorem equation, a square plus b square equals c square, where a, b, and c are natural numbers. The numbers a, b, and c are called Pythagorean triplet. For example, when we have 3 square plus 4 square equals 5 square. The numbers 3, 4, and 5 are Pythagorean triplet. In general, we have like this. For any natural number m that is greater than 1, we have this Pythagorean equation. The square of 2m plus the square of the quantity m square minus 1 is equal to the square of m square plus 1. So, this 2m, the quantity m square minus 1, and the quantity m square plus 1 forms a Pythagorean triplet. Note that the quantity 2m and the quantity m square minus 1 are the bases of the left side, while the quantity m square plus 1 is the base of the right side. Example 1. Write a Pythagorean triplet whose smallest member is 8. The three numbers of Pythagorean triplets are the 2m, m square minus 1, and m square plus 1, where m is a natural number. The number 8 here, being the smallest, may assume the first two values. That means this 2m and the m square minus 1. Then solve for m, hoping that the m would come as a natural number. So let's begin with the first value, 2m. We equate this to the number 8. So we have 2m equals 8. Then let us solve for m. We divide the equation by 2, so we will get m equals 8 over 2. And the quotient is 4. So m here is 4, which is a natural number. We can use this value now to solve for the other members of the triplet. Let's begin with the m square minus 1. We substitute the number 4 to m. So this becomes 4 square minus 1. 4 square is 16, then minus 1, and the answer is 15. This is the second member of the triplet. What about for m square plus 1? We substitute the number 4 to m, so this becomes 4 square plus 1. 4 square is 16, then plus 1 equals 17. Therefore, the Pythagorean triplet is, first member is the number 8, followed by 15, then 17. Example 2. Find a Pythagorean triplet in which one member is 12. The three numbers of Pythagorean triplets are the values 2m, the m square minus 1, and m square plus 1, where m is a natural number. In this case, the number 12 may assume any of the three values. Then we solve for m. Let's begin with the 2m equated to number 12. Then we solve for m. We have m equals 12 over 2, and the answer is 6. And 6 is a natural number. We can now use this value to solve for the other members of the triplet. Let's begin with the m square minus 1. We substitute the number 6 to m, so we have 6 squared minus 1. 6 squared is 36, then minus 1. This is equal to 35. This is the second member of the triplet. Next value is the m squared plus 1. We substitute the value 6 for the m, so we have 6 squared plus 1. Then this becomes 36 plus 1. Finally, the total is 37. And this is the third member of the triplet. So the Pythagorean triplet is 12, 35, and 37. There is one note here. All Pythagorean triplets may not be obtained using this form, meaning the three values here. For example, another triplet 5, 12, 13 also has 12 as a member, but this triplet doesn't follow this form. Hi everyone. Today we're going to study Introduction to Square Roots. Finding the square root of a number is the inverse operation of squaring. Let's see some examples. We know that 1 square equals 1. Therefore, square root of 1 is 1. 2 square equals 4. Therefore, square root of 4 is 2. 3 square equals 9. Therefore, square root of 9 is 3. Let's see this example now. 9 square equals 81. Next, the square of negative 9 equals 81. In this example, the square roots of 81 are 9 and negative 9. We can see that there are two integral square roots of a perfect square number. However, we shall take up only positive square root of a natural number. The positive square root of a number is denoted by this symbol. This is the square root symbol. Let us see this table, and this is about the square root of 1 equals 1, square root of 4 equals 2, square root of 9 equals 3, square root of 16 equals 4, square root of 25 equals 5, square root of 36 equals 6, square root of 49 equals 7, square root of 64 equals 8, square root of 81 equals 9, square root of 100 equals 10. The numbers 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100 are called perfect square numbers. Example 1. The area of a square is 144 square centimeters. What is the side of the square? The formula for the area of a square is A equals S square, or we say that the area equals the square of the side. In the problem, given is the area. We substitute this value to A. So we have now 144 equals S square. By this equation, we can say that S is the square root of 144. In symbol, we can write S equals square root of 144. And we can simplify this into 12. S equals 12 centimeters. This is the answer. Example 2. What is the length of a diagonal of a square of side 8 cm? Look at our figure here. We have the square ABCD. One side is given as 8 centimeters. That means all sides are 8 centimeters. This is the diagonal D. Notice that we have the isosceles right triangle ABC. Then we can use the Pythagorean theorem. The square of the side AB plus the square of the side BC equals diagonal, that is squared. Then we substitute the values. AB is 8, that is squared, plus BC is also 8, that is squared, equals D square. 8 square is 64. This is also 64. When we get the sum, we will have 128 equals D square. In this equation, we can say that the diagonal is the square root of 128. In symbol, we write D equals square root of 128. Then we simply attach the unit of measurement, centimeter. Example 3. In a right triangle, the length of the hypotenuse and a side are 5 centimeters and 3 centimeters respectively. Can you find the third side? In our figure here, the hypotenuse being the longest side, we put the 5 centimeters. Then one of the side is given as 3 centimeters. We need the third side and we name this as X. By Pythagorean theorem, we write now 3 square plus x square equals the square of the hypotenuse. We simplify 3 square as 9, 5 square is 25, then we copy the x square. We isolate now this x square. 9 is transposed to the right. 25 minus 9 is 16. So x square equals 16. We want the value of x. By this equation, we say that the value of x is the square root of 16. In symbol, we have x equals square root of 16. And finally, this is 4 centimeters. Hi everyone. Today we're going to study finding square root through repeated subtraction. Remember that the sum of the first n odd natural numbers is n square. That is, every square number can be expressed as a sum of successive odd natural numbers starting from 1. Now, to find the square root small n of a number capital N, we can subtract successive odd numbers to capital N starting from 1 and obtained 0 at nth step. Example 1. Find the square root of 81 by repeated subtraction. We subtract successive odd natural numbers that starts at 1 from 81. Then we get the value of small n from the nth step. So we copy this 81 down here, then minus 1. This is the first step. And the difference is 80. Then this 80 we subtract by the next odd natural number, which is 3. 80 minus 3 is 77. We take 77 minus the next odd natural number, which is 5. 77 minus 5 equals 72. Step 4, 72 minus the next odd natural number, which is 7, equals 65. Step 5, this 65 minus the next odd natural number, which is 9, equals 56. Then step 6, this 56 minus the next odd natural number, that is 11, equals 45. Step 7, 45 minus the next odd natural number, which is 13, equals 32. Step 8, this 32 minus the next odd natural number, that is 15, equals 17. Then step 9, 17 minus the next odd natural number, which is 17, equals 0. When we reach 0, we stop here. The n, or capital N, that is 81, comes to 0 at the 9th step. Therefore, we say that the square root of 81 equals 9, because there are 9 steps before we reach 0. Example 2. Find the square root of 25 by repeated subtraction. We subtract successive odd natural numbers that starts at 1 from this number 25. This is our capital N. Then we get the value of small n from the nth step. So step 1, this 25 minus 1, we get 24. Step 2, 24 minus the next odd natural number, which is 3, equals 21. Step 3, 21 minus the next odd natural number, 5, equals 16. Step 4, 16 minus the next odd natural number, which is 7, equals 9. Then step 5, 9 minus the next odd natural number, which is 9, equals 0. And from here we stopped. The capital N, that is 25, comes down to 0 at the 5th step. Therefore, the square root of 25 equals 5. Hi everyone. Today we're going to study finding square root through prime factorization. Let us see this table. We have prime factorization of a number in one column. On the next column, we have the prime factorization of its square. Let's have one example, that is the number 6. And the prime factors of 6 are 2 times 3. The 6 has a square of 36. Now the prime factors of 36 are 2 times 2 times 3 times 3. Another example, the number 8. The prime factorization is 2 times 2 times 2. 8 square is 64. And the prime factorization will be 2 times 2 times 2 times 2 times 2 times 2. Another example, Number 12. Prime factorization is 2 times 2 times 3, while 12 square is 144, and the prime factorization is 2 times 2 times 2 times 2 times 3 times 3. Next example, 15, and the prime factors are 3 and 5. 15 square is 225, and the prime factorization is 3 times 3 times 5 times 5. One thing that we will note here is the prime factors of a square numbers come in pairs. Now, to find the square root of a perfect square number, capital N, through prime factorization, then this number n we can write like this. N equals a sub 1 times a sub 1 times a sub 2 times a sub 2 times a sub 3 times a sub 3 times up to times a sub n times a sub n, where a sub 1, a sub 2, a sub 3 up to a sub n are prime factors of capital N that come in pairs. Now, we can write this capital N into like this. The square of a sub 1 times the square of a sub 2 times the square of a sub 3 times up to times the square of a sub n. By law of exponent, we can simplify the right side into like this. The square of the quantity a sub 1 times a sub 2 times a sub 3 times up to times a sub n. So, the square root of capital N equals a sub 1 times a sub 2 times a sub 3 times up to times a sub n. Example 1. Find the square root of 324 by prime factorization. First, we write the 324 down here, then we write the prime factorization. So we have 2 times 2 times 3 times 3 times 3 times 3. Notice that the prime factors are coming in pairs. So we can rewrite the right side into 2 square times 3 square times 3 square. We can simplify the exponent into the square of the quantity 2 times 3 times 3. And from here we can write now the square root of 324 equals this base, and that is 2 times 3 times 3. Finally, the product or the square root of 324 equals 18. Example 2. Find the square root of 6,400. We write the number here, then we list all the prime factors. And here is the prime factorization. 2 times 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 5 times 5. Notice that the prime factors are coming in pairs. Then we can simplify this into 2 square times 2 square times 2 square times 2 square times 5 square. We can simplify further the exponent into like this. The square of the quantity 2 times 2 times 2 times 2 times 5. Then we can now show that the square root of 6,400 equals the base 2 times 2 times 2 times 2 times 5. And the final product is 80. Example 3. Is the number 90 a perfect square? Note that a perfect square number is a number whose prime factors come in pairs. So the number 90, the prime factorization is 2 times 3 times 3 times 5. Notice that the prime factors 2 and 5 do not occur in pairs. Therefore, 90 is not a perfect square. Example 4. Find the smallest number by which 9,408 must be divided so that the quotient is a perfect square. Find the square root of the quotient. Let's write the 9,408 here. Then we write the prime factorization. So we have 2 times 2 times 2 times 2 times 2 times 2 times 3 times 7 times 7. Notice that some factors are coming in pairs except the factor 3. Therefore, this 9,408 we divide by 3. And the quotient is 3,136. To answer the first question here, the smallest required number is this number 3. Now, what about the quotient? We take the square root of the quotient 3,136. So the prime factorization is 2 times 2 times 2 times 2 times 2 times 2 times 7 times 7. And we can see that the factors are coming in pairs now. So we rewrite this right side into 2 square times 2 square times 2 square times 7 square. We simplify the exponent into the square of the quantity 2 times 2 times 2 times 7. Then we can show that the square root of 3,136 equals 2 times 2 times 2 times 7. And the product is 56. Hi everyone. Today we're going to study finding square root by division method. If a perfect square is a 3-digit or a 4-digit number, then each square root will have 2 digits. Let's see some examples. The square 100 and the square root is 10. This is actually the smallest 3-digit perfect square. What about 961? The square root is 31. And this 961 is the greatest 3-digit perfect square. Next square is 1024 and the square root is 32. This 1024 is the smallest 4-digit perfect square. The number 9801 is the largest or the greatest 4-digit perfect square, and the square root is 99. Then we generalize. If a perfect square is of n digits, then each square root will have n over 2 digits if n is even, or n plus 1 over 2 if n is odd. The use of the number of digits in square root of a number is useful in finding square root by division. Let's find square root by division method. Let's discuss this method through an example. Let's say find square root of 529 by division method. Step 1. We place a bar over every pair of digits starting from the digit at ones place. If the number of digits in it is odd, then the leftmost single digit 2 will have a bar. In here, our number is 529, so we put 1 bar to the number 29 and 1 bar to the number 5. We can see that there are 2 bars here that represent 2 digits for the square root value. Then step 2. We find the largest number whose square is less than or equal to the number under the extreme left bar. In here, this is number 5. Note that number 5 is between 2 square and 3 square. But in here, we're going to take the base 2. We take this number as the divisor, and the quotient with the number under the extreme left bar as the dividend. In here, it is 5. So, let us divide and get the remainder later. So, this is what we'll do. We divide this 5 by the number 2. And the answer is 2. Then we multiply 2 times 2 becomes 4. When we subtract, we will get the remainder 1. Step 3. We bring down the number under the next bar. In this case, it is 29 to the right of the remainder. So, we have now the new dividend 129. Step 4. We double the quotient and enter it with a blank on its right. In here, our quotient is 2. When we double, it becomes 4. And then, we put a blank after number 4. We need a digit for this blank. Step 5. We guess a largest possible digit to fill the blank, which will also become the new digit in the quotient, such that when the new divisor is multiplied to the new quotient, the product is less than or equal to the dividend. We're going to do here trial and error. Suppose in the blank, we write number 2. So we have 42. Since we write here 2, we're going to multiply this 42 by that same digit 2. 42 times 2, we will have 84. When we compare 84 by 129, this is much lesser. So let us see another number. Suppose we put 3 after the number 4. So this time we have 43. Since we write here 3, we are going to multiply 43 by 3. And the product is 129. And from here we can see that this value is equal to the new dividend. So in here, we're going to choose the number 3. When we finalize and we write here number 3, same value 3 we will write on top of this 29. So the previous quotient of 2 becomes 23. Then we get the remainder. That means this 129 here we subtract by this new dividend and we get 0. And step 6, since the remainder is 0 and no digits are left in the given number, therefore we stopped. Then we conclude that the square root of 529 equals 23. Example 2. Find the square root of 4096 by division method. Step 1. We place a bar over every pair of digits starting from the digit at ones place. If the number of digits in it is odd, then the leftmost single digit 2 will have a bar. Our number here has 4 digits. So that means when we group them, there's one bar on top of 96, another bar on top of 40. We find the largest number whose square is less than or equal to the number under the extreme left bar. In this case, we have here 40. Notice that 40 is between 6 square and 7 square. But in this case, we will use the number 6. We take this number 6 as the divisor and the quotient with the number under the extreme left bar as the dividend. Here is 40. So, we divide this 40 by 6. We will get 6. 6 times 6 is 36. Then when we subtract, we will get the number 4. The remainder is 4. Step 3. We bring down the number under the next bar, which is 96. So we have now the new dividend, 496. Step 4. We double the quotient and enter it with a blank on its right. The number 6, we double, it becomes 12, then there is a blank after the number 2. We need a digit here. Step 5. We guess a largest possible digit to fill the blank, which will also become the new digit in the quotient, such that when the new divisor is multiplied to the new quotient, the product is less than or equal to the dividend. So let's say for this 12, the next digit is 4. Since we write here 4, the 124 is multiplied by 4, and the product is 496, which is equal to the new dividend here. So we write and finalize the digit 4 here. At the same time, one digit 4 is coming after number 6. So the new quotient now is 64. Now we get the remainder. This 496, we subtract by this value 496. And the difference is 0. Then we stopped. Step 6. Since the remainder is 0 and no digits are left in the given number, therefore, the square root of 4096 is 64. Hi everyone. Today we're going to study estimating the square root of a number. Let's have the number of digits of the square root. In the division method of finding square root, we use bars to find the number of digits in the square root of a perfect square number. Let's have the square root of 529, and that is 23. Another example, the square root of 4096. The answer is 64. In both the numbers 529 and 4096, there are two bars, and the number of digits in their square root is 2. Then we generalize. The number of bars on the given number tells the number of digits in the square root. Let's have another example, the square root of 14,400. When we put the bars, it will look like this. One bar for 00, another bar for 44, one bar for the number 1. Since there are 3 bars, the square root will be of 3 digits. Let's discuss finding a perfect square nearest to a number. Let's have some examples. Example 1. Find a least number that must be subtracted from 5,607 so as to get a perfect square. Also, find the square root of the perfect square. We write the 5607 here. Then we will do the division method. We put the bars on the 07, another bar for the number 56. Then we take the square root of 56. Remember that 56 is between 7 square, which is 49, and 8 square, which is 64. So the square root of 56, we write here 7. So the square root of 56 is 7. We write here the number 7. We multiply 7 by 7, we will get 49, and the difference is 7. Then we bring down the 07. And from here, we're going to double 7 into 14, and there is a blank after the number 4. This blank represents a digit. We want to know this digit, and we can do trial and error. We can write, let's say, 4. So the 14 blank becomes 144. Since we write 4, we will multiply this by that same value or same digit, which is 4. And the product is 576. After that, we put the digit 4 on the blank, here, and also on top. So the previous quotient of 7 now becomes 74. Then we subtract 707 by 576. And the answer is 131. With this solution, it shows that 74 square is less than 5607 by the remainder 131. So that means the required perfect square is 5607 minus the remainder 131, and the answer is 5476. So this is the perfect square number. So when we take the square root of this 5476, the answer is 74. Example 2. Find the greatest 4-digit number which is a perfect square. Note that this 9999 is the greatest 4-digit number. Let us try to get the square root of this number. Let's do the division method. We put the bars like this. Then we take the square root of 99. Notice that 99 is between 9 square and 10 square. 9 square is 81, 10 square is 100. So this value of 9 we write here. When we take the square root of 99, the answer is 9. We multiply 9 by 9, so we have 81. And when we subtract, the answer is 18. We bring down now the 99. So the new dividend, 1,899. Next step, we double this number 9. It becomes 18. Then we put a blank on the digit after 8. We want to know this digit by trial and error. Let's say we put 9. Then we multiply the 189 by 9. And the product, 1,701. Then we fill in the blank here with the digit 9. Also, we put the same digit on top. Then we subtract 1,899 minus 1,701. And the difference, 198. It shows that 99 square is less than 9,999 by this remainder, 198. So for us to get the perfect square, 9,999 minus the remainder, 198. And the answer is 9,899. 1,801. That means this is the greatest 4-digit number which is a perfect square. Notice that the square root of 9,801 is equal to 99. So our answer is this number. Example 3. Find the least number that must be added to 1,300 so as to get a perfect square. Also find the square root of the perfect square. Let us do division method to get the square root. Then we put the bars. Notice that in the first bar, the number is 13. The number 13 is in between 3 square, which is 9, and 4 square, which is 16. So we use this small number in here, the number 3. So the square root of 13 is 3. 3 times 3 is 9. When we subtract, the answer is 4. We bring down the 2 zeros. And next step, the number 3, we make it 6 with a blank after 6. This blank is a digit. By trial and error, we can write any number and check. Suppose we have 6, we write in the blank the number 6 also. Then we multiply 66 by 6. The answer is 396. And from here we can write the number 6 here, also same number 6 on top. That means our new quotient now is 36. Then 400 minus the 396. And the difference is 4. That means the 36 square is less than 1,300 by 4. But look at the problem. We want a small number that must be added to 1,300. That means we're going to consider the first whole number that must be squared. What about 37 square? And this is 1,369. That means we're going to consider this 37 square. So the least number to be added, this 1,369 minus 1,300, and the answer is 69. And that means the perfect square number that we're looking for is this 1,369. And the square root of this is 37. Hi everyone. Today we're going to study square roots of decimals. Let's have some examples. Example 1. Find the square root of 17.64. Step 1. We put bars on the integral part. In this case, we have 17 of the number in the usual manner, and place bars on the decimal part. We have here 64 on every pair of digits beginning with the first decimal place. The first decimal place is 6 and the second is 4. That means there is one bar for the number 64, another bar for the number 17. Then we put the division symbol. Step 2, we now proceed in a similar manner. The leftmost bar is on the number 17. Then we take the square root of 17. Notice that the number 17 is between 4 square and 5 square. So we will use the smaller value. This number 4, we will take this as the divisor, and the number under the leftmost bar as the dividend. So we write number 4 here and also here on top of 17. We multiply 4 by 4, we will get 16. When we subtract, the difference is 1. Step 3, we write down the numbers from the next bar to the remainder. The new dividend becomes 164. Then step 4, we vertically copy the decimal point to the quotient. The decimal point is here, so we copy this point on top. Step 5, we double the divisor and enter it with a blank on its right. The divisor is 4. When we double, it becomes 8. Then there is a blank after 8. Step 6, we guess the digit A for the blank, such that 8A times the A should be less than or equal to the new dividend. So, by trial and error, we can say 2. We multiply 82 by 2, and the product is 164, which is equal to the new dividend. Therefore, the new digit is 2. So we write the digit 2 here, also the number 2 on top of 64. So the new quotient will be 4.2. Then we divide and get the remainder. That means this 164 minus this value here, that is 164 also. And the difference is 0. Step 7. Since the remainder is 0 and no bar left, then we conclude the square root of this 17.64 equals 4.2. Example 2. Find the square root of 12.25. We write the bars. So one bar for the number 12, another bar for 25. Then we show the division symbol. Let us take the square root of 12. We know that 12 is between 3 square and 4 square. So we consider the smaller value. So we write number 3 here and also here. 3 times 3 is 9. Then we take the difference and the answer is 3. Then we copy the decimal point on top. Then we bring down 25. So the new dividend is 325. Next step, we double this number 3. It becomes 6. Then there is a blank after number 6 that represents a digit. By trial and error, we can show that 6, we can write 5, so 65. Then we multiply 65 by the number 5. And the answer is 325, which is equal to the new dividend. In that case, we write now the digit 5 here and also 5 on top of this number 25. Then we subtract 325 by this value here, 325. And the answer is 0. Since the answer is 0 and no more bar left on the number, we stopped. Then we conclude that the square root of 12.25 equals 3.5. Example 3. For the square root of 176.341, how do we put the bars in the step 1? This is how we're going to put the bars. For the integers, there is one bar for the number 76, another bar for the number 1. On the decimal part, we put one bar to the first two decimal places, 3, 4. Another bar for the number 1. In this case, we can add 1, 0. So we put one bar to the number 10. So this is the answer.